WJAM Scopus belum tahu. Kami tengah nak siapkan punya
WJAM okey lah. Syarat sekarang kan dia nak submit, nak apa graduate, dia kena at least untuk WJAM atau Scopus. Index lah.
selalu yang ni orang punya kalau dulu lah macam mana tak ada charge. Sekarang kami charge lah sebab ada factor. Kalau tak ada charge memang last resort lah siapa yang nak grad habis lah kat sini.
Dulu saya ada yang UTM itu tak index lagi. Jadi nak cari orang atau susah sebab tu orang pun nak dia jadi dah ada dah okey dah.
Tapi yang saya buat saya itu bagus.
Dia begitu yang private ni kan itu bagus.
Dia memang saya tengok cara manage tu bagus.
Memang kata pasti begitu ada tapi ada lagi bawah ni.
Macam saya dulu training tu saya ada table kan.
Yang saya tu dia lain tapi bawah UTM kan. Yang ni dia bawah association. Tapi apa tu private yang private
Okay, Assalamualaikum warahmatullahi wabarakatuh, and welcome back to the second session for the International Conference on Future Trends in Welding, Joining and Additive Manufacturing 2023. We will start the invited speaker session 2 by Associate Professor IRTS Dr. Muhammad Rizal bin Al-Kahari with the topic of current and future trends in additive manufacturing, 3D printing. A little bit about Dr. Muhammad Rizal. Dr. Muhammad Rizal is a manager at the Center of Excellence, COE, Office of Deputy Vice Chancellor, Research and Innovation of University Technical Malaysia Melaka UTM. He also the head of additive manufacturing, 3D printing and innovation laboratory at the Faculty of Mechanical Engineering of the university. Without further ado, I would like to welcome Dr. Muhammad Rizal.
Assalamualaikum dan selamat petang. Thank you, Chairperson, the organizer, and Prof, Doctor, and all the participants. Thank you for the invitation for this afternoon. Okay, today my name is Muhammad Rizal Kahari from University Technical Malaysia Melaka. So I will be presenting the title Current and Future Trends in 3D Printing and Additive Manufacturing. Okay, currently I'm the manager at the Center of Excellence and also the head of Additive Manufacturing or 3D Printing lab at the university. Okay, so Melaka, so we go very fast. Just an introduction. Located in Melaka, UTM, one of the technical university. So during the presentation, I will highlight some of the equipments that we have also. So maybe if you are interested, you can come and visit and contact me in the future. Okay, so this is the outline of my presentations. Initially, I will give some introduction on 3D printing, additive manufacturing. Very brief. I believe everybody here very familiar with the process, but there are a few things that I would like to highlight so that it will be a continuation that of what I'm will be explaining throughout the presentations. Okay, and then I will highlight the recent progress and perspective of 3D printing or AM. And then some of the works that has been done by our team at UTM, and specifically I will discuss a bit on wire-up additive manufacturing, one of the focus of my area of research. And then by that later I will conclude the presentation. Okay, so just an introduction. At UTM we have AMRG, Additive Manufacturing Research Group, which consists about almost 20 staff from various backgrounds. We do focus on various aspects of the research, for example, DFMM, DFAM, composite materials, process improvement, monitoring and control, vibration, absorption, rehabilitation, preservation, tribology, remanufacturing, and others. So the teams come from different area, but when we have this group, we try to utilize AM and 3D printing so that we can apply it for different applications and study from different perspectives. Okay, so everybody knows about this. We have 7 classification of AM. We have binder jetting, directed energy deposition, material extrusion, sheet lamination, material jetting, wet photomerization, and powder bed fusion. These are the classification that has been given by ASTM. So my presentation mainly mostly covered for material extrusion, directed energy deposition, and powder bed fusion. So throughout my work and my team, most of us focus on this. Of course, we have the machines, but more on the teaching and learning. But the one that we are doing for research basically focus on DED, material extrusion, and powder bed fusion. So there are a lot of a number of classification for each of these group. But of course, once I focus more on wire up additive manufacturing, later on I will focus more on the up welding. Okay, so basically this is the difference between the process, the way how it how the materials are being laid layer by layer, and then these are some of the facilities that we have at the university. We have binder jetting, selective layer sintering, directed light processing, microjetting, stereolithography, fixed deposition modeling, and then for metal we have SLN, the open source system from Aurora. Then we also have recently last year, one of the faculty we have purchased SLS and just this year, early this year, we have received our robotic WJAM, which we use CNT, and then we also utilize a lot the customized that we have developed through the project, microplasma WJAM. This one is actually being customized from open source system. So basically, the things that I explained, we utilize a lot of based on these machines. Okay, so if you look at the recent progress and perspective of 3DP or AM, we can see that there is an increasing number of people that start using 3D printing. If you look at the reports, it is expected that this number will be increased further in the future. So having this team, I guess, is the right time that we can focus in the area. Basically, in Malaysia, I guess, in terms of the implementations, even though there are a certain number of companies try to offer services on this, but when we would like to apply for real industry parts, there are a lot of issues. Okay, and then it has been said that there is a strong demand also for metal part, even though it is expensive. Many companies are looking forward to have this sort of system in the future. Then, in terms of the application, you can see that a number of significant projects in the world right now. For example, we have a various of complex parts for engine parts that utilize metal 3D printing. We have this year, a few months back, we have the world's first 3D metal printed rocket by relativity space. Sorry for that. I guess in May, they just, of course, there are some issues, but the rocket successfully has been built by using the wire up additive manufacturing. And then we have the world's largest building in the Dubai. Then we have the world's first 3D metal printed bridge in Amsterdam last year. So you can see that the trends, people are start using WJAM, 3D metal printing for various applications. So even though there are a lot of challenges and to implement 3D metal printing in industry, for example, in terms of cost, technical obstacles, standards, material performance, which are not in par with the normal material, and then but still people start to explore the possibilities, and then lack of know-how and the perception of people, because we start to use 3D metal printing to replace one of the critical parts. People start asking the reliability, the standards, the risks that will be faced, and so on. So these are the challenges, but these open the new opportunities for our research later on. Okay, so these are some of the opportunities that we can cater. For example, these are some from other studies that has been reported recently. For example, there is issues with distortion, delamination, and cracking. This has been highlighted by Prof. Jupiter this morning about where he explained from the aspect of simulations. So, and then why it is related to the thermal history. during the laser irradiation, for example, in SLS element, there is a repetitive heating and cooling. So the thermal history will affect the thermal, what we call, the final part will experience heating and cooling, which will affect the quality of the part in terms of the mechanical properties, the porosities, the quality, the surface finish, and so on. So these are the things that still ongoing research that we can highlight and produce good result for this. Okay, so other challenges and opportunities in terms of the design. Sorry, I keep mistakenly pressing the what you call the pointer. Okay, in terms of the design, there is a low geometrical tolerance, inconsistent part quality, and then there is inaccuracies that will affect the quality of final parts. But from another perspective, this can be the opportunities for us to do the research, and then we can reduce a lot of weight, improve thickness and consolidation of parts in order to produce final parts. Okay, so next I will highlight some of the research that has been done at UTM related to AM. We do focus on a few aspects. For example, in terms of the design, monitoring, not fully controlled yet. We are just more on the monitoring side, but looking forward to go for monitoring and control, and properties of behavior, and then we try to apply at different applications, and then there are team also focusing more on the developing a new materials, composite material. We try to produce our own filament, for example. And then there are teams also that focus on the process improvement, post-processing operated parts by having the vacuum and vibration, assisted FDM, and integrated pressing. These are some of the examples that I will explain further, very brief. Because I believe at what time we have to, because we started a bit late just now. 2:30. Okay. Okay, we go very fast for this one. So these are some the detail. Maybe you can refer to some of the paper that I highlight here. For example, one of my students focusing how we can implement or integrate trees in terms of the design. Trees during the FAM. And then, of course, try to see this one. And then there are teams also develop a low-cost 3D metal printer by using open source system, the one that we have just now. And then then it receives some sort of coverage in 3dprint.com previously. So we use the open source system, normal open source system. We do modify it based on the requirement for welding purposes. So based on that, of course initially it's not very successful, but now alhamdulillah we managed to create a more complex structure based on this. And then there are teams also looking at the DFAM, the ability of the parts to produce with the limited or required behavior. For example, at what range it is suitable or not. So we do some sort of research on this. And then we do try to improve the process by integrating some sort of pressing, vacuum, and then liquid depositions. So these are some of the modification that has been made on the normal 3D printing process. Okay, this one, for example, we have a post-processing by using cool vapor, we call it. So this one is published in the this journal. And then another issues in AM is that we would like to understand the process further by monitoring it. So if you look at in details, previously researchers try to understand by having by monitoring closely at the process. So based on the previous research, you can see it is not very clear due to the limitation that they have like at that time. So what we did is that we have some sort of this setup, and then we able to monitor closely. Maybe this one, maybe can display some video. Okay, you can see actually the laser. This is during the SLS of SLM. So the laser is about the size of my laser pointer here. It's in front here. So it will move. So based on that, we can monitor the process closely and try to relate to mechanical properties. So these are some of the labels that indicate the process itself. So at these different what we call parameter. So when we use different parameter, for example, at a higher speed, we can observe the fundamental issues that we can investigate and relate to the mechanical properties. And then from here also we can check the temperature because the properties is highly relevant to the temperature that being experienced by the process. And then the microstructure, because once we observe it, we would like to relate to the common mechanical properties. So we try also to observe for WAM, but it's still in progress. Last time for SLS or SLM process. And then some other studies related to the materials. We try to use different materials and recycle materials and looking forwards at this one is for SLS, SLM for plastic-based material. And then there are groups also that focus on developing a new composite materials. At UTM we have this twin screw filament extruder. We can actually produce a new filament by using these machines, but still at the preliminary stage. And then there are team also try to relate the tribological properties by Dr. This one is by PM Dr. Fazli, the teams. And then there are also teams that try to work with Persil. As we know, Malacca is a lot of history there. It begins, history of Malaysia begins in Malacca. So at Persil, Perbadanan, I didn't remember the full name. Something related to the museum. That we remember what it stands for. So we try to preserve some of the historical artifacts by using AM. Okay, we also have some work on rehabilitation. We do work together with Perkeso. We try to produce what we call the socket prosthetic leg here, and to replace the normal process. As you can see, the normal process it takes a very long, and cost the cost is high, and then it takes about 2 weeks to ensure that the material is fully hardened and can be used. But now the time can be reduced within 8 hours, 10 hours. Within 1 day, we can produce the prosthetic leg directly. Okay, so background a little bit on WJAM. Wire up additive manufacturing is very much related to the joining process because welding is a joining process, but now we try to use it as a additive manufacturing process where we lay welding process layer by layer. But of course, we have to make sure that we use this suitable parameters, suitable settings so that we can produce a good part. So these are the machines that we have used last time. We have developed in the lab. Then, of course, initially we can see we don't even manage to get the 3D structure. But after the sum of the optimization and the process that has been done, improvement that has been done. We can recently, alhamdulillah, we can get a more consolidated structure right now. Then these are some of the properties that we have used, and then of course after that we go for the microstructure analysis, studying how the hardness, the microstructure differ from one parameter to another. So these are some of the microstructure. Then of course we are looking forward to relay. Just now we discussed among the few researchers how we can relate this during the processing, so that once we have this data, we can give feedback, so that we don't have to wait until the process completed. We can predict what will happen later on. Currently we are using some sort of thermal camera image to get the information. So these are some of the temperatures that can relate. You can see when there is a very high temperature here, this area will fail, and we cannot produce data exactly that has been drawn from the what we get from the CAD. Okay, another application is that we can use it for, we are currently using it for remanufacturing. One of our projects, we would like to repair. If you are familiar, remanufacturing is we would like to repair. In other words, it's a repair to restore the damaged parts. So what we did is that we have we use a 3D scanner to get the 3D cloud data, and then use software to repair it, then send it to the robot WJAM and try to remanufacture by using WJAM. Of course, the quality, we need to still to post-process it. We need to machine it to ensure that we can get a smooth surface. Okay, these are some of the parts that we have produced. You can see currently, initially when we start WJAM, we cannot even get the 3D structure, consolidated structure, because once the temperature is very high, it will remelt the bottom layer again and again. So currently, just recently, we managed to get a more, not so complex yet, but we're going towards that. Hopefully, in future, we will be successful. So it's part of the blade shape, and then we something like hollow, but we put some angle here so that it will to check whether it is feasible or not. Okay, so just now I have explained basically in here current project that has been done. So in future I predict and then there are a lot of studies shows that there will be a lot of integrations with other technologies, for example AI, simulation, cloud, system integration, sustainability concept, robotics, and Internet of Things to improve the process itself. Currently, maybe for example, maybe we are talking about monitoring, but what more important is that after monitoring, we would like to control. We would like to ensure that prior to the process completed, we already know that this might be can cause problem. So it is better that we try to do some setting, improve the setting and so on before it is completed. So maybe there is a need to integrate some sort of real-time monitoring and control, maybe real-time NDT with the temperature measurement and so on. So in future, I believe these are the trends. Just now, Prof. Bibita also talking about generative design. So these are the things that the research area that we should be heading towards. And then maybe in the future also, most of the application right now more on the desktop scale. So maybe in the future, we can see right now is concrete printing, warm bioprinting. So from massive to minute, maybe will be more what we call prominent in the future. And then there is a need to ensure that there is a system integration. You can see just now from my setup previously, maybe it is individually controlled. Yeah, we have to control a few things to get the data, for example. For in future, there is a need to integrate everything in the one machine. Of course, there is a need to understand AI, IoT, robotics, so that everything can be controlled together. Then in terms of the moving towards, we are talking about 3D printing or additive manufacturing, but out there people start already with the 4D and 5D printing. So these are the things that future the direction will be. Then hybrid and novel process, combination of several process, AM, SM and FM. What are they? SM is subtractive, FM is formative manufacturing. So, and also on the new and novel materials, I believe in future there is a tendency to use multi-materials, smart materials, biomaterials with the composite to enhance the process itself. Okay, so as a conclusion, additive manufacturing, also known as 3D printing, has captured the imagination of many technology observers and manufacturing professionals. And then the opportunities for fully utilized 3D metal printing are limited due to the printing capacity and investment costs compared to the 3D printing of other materials. However, the use of open source system may enable relatively acceptable part quality to be produced. So these are one of the ways that we can use to reduce the cost, but at the same time open up the new opportunities for other research areas. Metal 3D printing is getting more attention to be used in various applications. Although its utilization is still new and infancy stage, future trends shows it's a promising potential. So we should be heading towards that. Okay, so that's all from me. I would like to acknowledge all the researchers who are also contribute to some of the slide here, and to my team, my postgraduate students. Okay, that's all from me. Is there any question?
Thank you, Dr. Muhammad Rizal, for the amazing sharing session. So we would like to open a Q&A session if there are any questions. Okay, I think that's all.
Okay, thank you.
Okay, thank you, Dr. Rizal.
Ada.
Dr. Rizal, yang kan tadi the future trend tu kan, on the, I mean, for the repair yang just now we discussed tu kan, I mean, on what state are we now in Malaysia compared to dalam developed countries?
Okay, so the use of remanufacturing is still new. In fact, for one of our research grant, actually we do visit for remanufacturing. Actually, we have KKP grant, Konsortium Kecemarangan Penyelidikan, with UKM, UTM, and UTM. We do visit companies in Japan, actually, how they do the remanufacturing. Not only in Malaysia, even though at the worldwide stage, the way they are doing remanufacturing is manually, actually. I did visit a few companies in, for example, Mazak, Komatsu, and a few others. They are doing the remanufacturing manually, meaning to say they have to use the skilled workers from the welding background. And then when we are talking about AM, they are still new for them. They are talking, maybe they know about metal 3D printing, but to integrate metal 3D printing for reman is another area which are not well explored yet. And many people are using manually to do reman. So these are the things that we can go forward in the area. It's a good opportunity, research opportunity for research. But of course, there are a lot of issues here. For example, the simplest one, we have to make sure that what we call the origin, or to make sure when we deposit the material exactly on the same place. Yeah. So this is the common issues. Another thing is that when we have the parts, when we are depositing the materials, there are parts where the heat accumulation will be inside the closed area. So that will create another issues. So once we say the issues or challenges, I mean there is a new opportunities. Okay, I think that's all. Thank you. Assalamualaikum.
Okay, thank you again to Dr. Muhammad Rizal. So next we will move to the next concurrent session that will be here until 3:30 p.m. Meanwhile, for the participant for academic industry meeting, will be at meeting room 1. That's all. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Good afternoon, distinguished guests and presenter. Today we will be starting our committee session, our third committee session of today. My name is Keval Pratama Prajadiana, and I will be acting as your session chair for the session. We'll be moderating this whole session. The presentation rules are the same like similar before. Each presenter are given 10 minutes of presentation time, and we will be given a mark when the time has been set for 8 minutes. And we will be followed by Q&A maximum for 5 minutes, so total should be not exceed 50 minutes. We will be starting with our first presentation. Is from Miss Siti Umrah Zainal, who will be presenting her research in regard compression analysis of triply periodic minimal surface or TPMS lattice structure between diamond and split P designed by numerical simulation. Miss Siti Umrah, the floor is yours.
Assalamualaikum. My name is Siti Umrah binti Zainal. I'm from University FTWJAM. Today I want to present my paper. The title of my paper is Compression Analysis of Triply Periodic Minimal Surface TPMS Lattice Structure between Diamond and Split Designed by Numerical Simulation. Before I go deeper, let me explain what is a lattice structure. Lattice structure is a repeating of your unit cell patterns to be arranged and fill up the array, the space using cell map. There are several types of unit cells such as TPMS, honeycomb, plate, and diamond. And lattice structure actually giving lattice structure actually can giving the benefit for industry, which is the benefit is lightweight, which is good in critical part, and can giving the good energy absorption, thermal management, and also integration. Based on the unit cell patterns, such as like I mentioned before, TPMS is the famous one because of the benefit is all around good in mechanical properties. So the triply. So my research is on the TPMS. So what is TPMS? TPMS is a triply periodic minimal surface, which is derived from the minimal properties of the geometry in the three different directions, where the mean curvature is equal to 0 at every point. An example of the TPMS, frequently you can see from the previous research. The famous one is the gyroid, diamond, and primitive. And the objective of my paper is to find out the compression behavior of the split P and diamond lattice structure, and also to discuss on how the lattice geometry configuration between both split P and diamond respond to exerted force. Split P is one of the TPMS lattice structure. And why I concentrate on the split P, because the attention on this kind of lattice structure is less attention on this kind of lattice structure. Okay, Von-Mises stress theory is related to the compression behavior. A linear elastic region is followed by plateau of a roughly constant stress before entering the final region. The final region is this densification. Each region has deformation mechanism, that can be determined by the loading and the geometrical structure of the specimen. Linear elasticity results from the lattice bending during initial loading. The lattice start to collapse. The cells of the lattice start to collapse when the critical stress or yield stress reach at the elastic buckling. Normally, the maximum point of from the first region. When the buckling create a small defect, so the plastic will collapse. So plastic deformation, which is in the region number 2, where the cells begin to collapse under coastal load while the stress level gradually increase. This called as a young modulus plateau, and the region number 3 is densification, whereas the stress is the specimen becomes rigid. Okay. TPMS design can be created using anthropology software, which is the specimen is in the cylindrical shape, the height 40 mm, the diameter is half of the height dimension, and the specimen will fit with the top plate and bottom plate. This is compulsory to get uniform distribution of load. And the diamond and split P unit cell size is diamond and split P unit cell size was 5 mm. Its strike diameter is about 0.8 mm. Okay, numerical simulation was analyzed through static finite element, which is employed by anthropology as well. Material that be chosen is stainless steel 316. The load applied gradually until reach a state of the equilibrium, and the distribution load that being used is 100 kilonewton on the top, and the placement retained at the bottom of the specimen, and all initial and damping forces were neglected during this simulation. Okay, result and discussion from the result that I received from the analysis. Von Mises stress recorded that split P has 55% higher than diamond. However, the maximum principal stress is lower, about 29% than diamond. So based on the result of von Mises stress, split P provide the high overall stress state which could withstand compression load, and split P is actually more ductile compared to the diamond. Meanwhile, diamond shaped lattice structure look like live give lower value of von Mises stress. However, diamond is very good in structural component behavior under loading condition. That means diamond is more stiffer than the split P. Okay, based on the result, it shows that diamond has lower von Mises value, but it has high stress concentration with significant tendency to cause plastic deformation at the uppermost layer. Von Mises are also known as the equivalent stress, which combine effect of a normal and shear stress. It is derived from the concept of distortion energy theory. When the shear stress or distortion energy of a ductile material reach its highest value, the yielding of the ductile material gets started. The failure of the ductile material happens when the yield reach to the elastic buckling to form a small defect, and then the cell will collapse. So the split P geometry properties and the split P geometry properties and has strong interconnectivity of the unit cell in the structure give to the von Mises stress value for high performance in mechanical properties.
2 more minutes, miss.
Okay, maximum principal stress analysis. A diamond and split pea show the high magnitude at the uppermost layer at the joint of the stride and plate. However, diamond has higher maximum principal wave 3,645 compared to split pea with 2,855 mpm. In comparison to the interconnected diamond-shaped unique cell, the structural behavior of the diamond actually is stiffer and under loading condition, and it's brittle. The principles occur along specific direction. The critical point at the joint area at upper layer is potential for failure due to the separation of atom in the planes. Fracture occur when the stress acid material alternate strength, and the critical area of the lattice structure need modification with appropriate reinforcement of modification the geometry to distribute the stress more evenly. Okay, displacement of deformation. Split pea record about 2.7 mm of displacement compared to diamond with 3.48 mm. The result shows that the split pea indicate small amount of total displacement of deformation, and split pea has ability to withstand the exerted load without compromising safety and efficiency. Stress can lead to deformation if it exceeds the material inherent strength. By understanding the compression behavior, shear stress play a significant raw material deformation at parallel to the cross-section area and can cause the layer to slide over another with the lead to deformation. So, von Mises, also known as equivalent, is a scalar value of stress used in structural analysis. Structural analysis to determine physical structures such as deformation, which has involved the application of the stress and strain theory. So as a conclusion, in overall, the split pea lattice structure is capable to withstand uniform exerted load and offer more effective carrying power, and resulting in a greater capacity for supporting stress compared to diamond. Von Mises stress and principal stress are two important concepts for analyze the stress distribution in lattice structure. Von Mises represent equivalent stress, particularly useful for prediction of yielding or failure of the data material. Meanwhile, the principal stress refer to maximum and minimum normal stresses acting on the lattice structure in a specific direction. So both of the concept actually is giving a crucial role to be used to optimization of designing by adjusting the structural geometry to ensure the stress level remain within acceptable limit. So by considering those things, by considering the von Mises and principal stress, the concentration area, the localized area that very critical can be adjusted, can be redesigned due to their safe and reliable structure, and to make it to enhance the performance due to the performance of the mechanical component. Okay, thank you.
Okay, thank you very much, Ms. Siti Umrah. Are there any questions from distinguished guests? We are open for a question. Okay, thank you.
Okay, I have two questions. One is I sort of expected the stress not to be concentrated at the end of the specimen where you mount the specimen, basically where the clamp is. I would expect in my mind that the stress would be uniform the specimen attached, the clamp. Because I'm wondering whether it could be due to like fixed nodal, like fixed displacement at nodal point that sort of constrict the displacement and like, causes the stress to concentrate over there, which like I was wondering whether the connection between specimen and the clamp is like a fixed displacement or it's like a sliding, like there's a freedom, planar freedom for the node to slide, because I would in my mind imagine that would be the
You mean the von Mises stresses?
no, the node that's fixed to the clamp, whether they have like a planar freedom, if fixed in like axial direction, but not in the perpendicular direction, because it seems to me that there's a fixed nodal displacement at the like the clamp flexible bed. I feel that that is what causes the stress concentration there. Okay, number two is what is the mass difference between the two specimens? Because it could be there's a difference in like the plasticity of the force is basically a difference in mass. So you can have to make sure the mass of the volume of both is the same. Then the geometry will be the difference between.
Okay. The first questions you expected that von Mises stress
Not concentrated.
concentrated.
Yeah, where
You mean the specimen is has that specimen has restraint displacement restraint.
yeah.
Okay, and then we do that. And then I did the compression analysis on it, and then it come up with the von Mises stress and the flexible principal stress. So the question is
whether the reason why there's concentration there is because the nodes they are not free to be displaced.
oh okay the concentration area.
Yeah, because basically when you compress there will be a radial expansion. Right.
Okay.
So maybe why there's concentration at top and bottom is because node is constricted. You cannot expand radially, so that's why.
Okay. Because alright. Okay. Because the analysis, the simulation analysis is under equilibrium state. It's not it's not until fracture. You know, they're only at the elastic region. So when you see the picture, it has only mentioned the knot is critical value at the critical value is at the knot. So that's, and by using the anthropology software, the simulation result is just at the region 1. It's not at the plastic deformation. It's not continue to the plastic and rupture. That's why you see the specimen is not kembang expand, yeah. And the second question is the volume. Okay. I did measure about the volume, and I did measure about the ratio of surface area to volume. Compares diamond and the split P. Split P has higher volume compared to diamond. So based on the result of the surface area ratio, the efficiency of the permeability and the efficiency of the split P actually higher. So split P has more surface area exposed, and I think this is the one of the reason why split P can restore the energy. So when restore the energy, that's why the value of the value of the Voronezh stress is higher compared to the diamond.
Okay, thank you very much. For the participant, has the presenter already answered the question? Sorry, Mr. It's already time for next presenter. Next presenter. Apologize. Okay, thank you very much, Miss Siti Umrah. Thank you for your presentation. And the next part is we will be calling the presenter, Miss Nur Elina Ezet binti Anwar, on the topic investigation on the thermal and wettability properties aided with shear test simulation of thin SN and bismuth solder alloy at low reflow temperature. Then the floor is yours.
Hello, good evening. I'm Nur Elina Ezet binti Anwar, and I'm from Taylor's University. Today I'll be presenting my paper entitled Investigation on Thermal and Wetting Properties aided with shear test simulation of SN solder at low reflow temperature. Alright, so this will be my outline throughout the presentation. So this will be my outline throughout the presentation, consisting of introduction, methodology, results, and conclusion. So as most of you know that the common solder is always the SNPB, or we call it the lead-based solder, which is very effective in connecting material with low melting point, along with good mechanical and wetting properties. But lead is said to be very toxic and can affect the environment and health, which is why we want to focus on the lead-free solder to be replaced from lead. Then we've considered zinc, aluminium, silver, indium, antimony, but the perfect choice we can come up with is the bismuth. Bismuth. So therefore, what motivates us to do this project is to investigate the properties of SNBI with different bismuth compositions. And another is to investigate the wetting properties, which is the spreading area at different reflow temperatures. And lastly is to stimulate mechanical properties of solder joint in terms of stress, strain, tensile strength, and ductility using ANSYS software based on different mechanical parameters such as velocity and temperature. I've made some comparisons between lead, bismuth, and also zinc in terms of the thermal, wetting, and mechanical. Most of the research made is based on their respective eutectic states. So between lead and also bismuth, bismuth has the best properties where the melting temperature is lower than lead, and the mechanical property shows higher values. Comparing with bismuth and zinc, which is another lead-free solder, once again bismuth shows the lower melting temperature compared to zinc And the mechanical properties of bismuth shows better values than zinc. So moving on to the methodology. As you can see here, I'll be discussing the solder preparations, the SC machine for thermal tests, spreading area for wettability tests, and also single lap shear tests for the shear strength. So as you can see here, these are the sequence of solder alloy preparations. It starts with weighing the tin and bismuth according to the bismuth compositions. Then the metals are heated out in the furnace for about 400 degrees Celsius, then hold it for about an hour, cooling it down. And then it goes through the remelting process where the solder will be placed on the hot plate to get the sample to be pressed using the hot press machine where no temperature will be required. Then the press sample will be formed into billets about 5 mm diameter. So then the billets will be used for the wettability test later on. So for the first experiment is to run the DSC machine with the leftover debris from the solder alloys. We can use about 5 milligrams of the to implement into the DSC machines for each of the solder alloys. So nitrogen gas will be used as it is in this medium because it is more stable. The sample will be placed in a sealed crucible and placed in the DSC machine. And the temperature is ranging about 100 degrees Celsius to 300 degrees Celsius, then back to 300 degrees Celsius to 100 degrees Celsius. Is so that we can have the phase diagram. We wanted the exo and endothermic peak of each of the solder alloys. And as for the wettability test, before placing the billets, we apply zinc chloride flux onto the copper substrate to avoid oxidation. Then the hot plate is wrapped with the aluminum foil, so the temperature of the aluminum foil will be monitored using the thermocouple to monitor the refill temperature before putting the solder billets. So each of the solder billets will be heated about 30 to 40 seconds, then it will be cooled off. So from there, the spreading area will be measured under the enhanced microscope that straight away just gives the spreading area. And for the single lap shear test, is being conducted under a simulation form So 3D geometry of a single lap shear joint was constructed using SolidWorks software according to the STM-D0102 standard. The geometry consists of 2 metal plates according to the dimensions shown here. And the copper was assigned as the substrate of the metal plates. Then the geometry will be applied to ANSYS to test the impact of the load applied. So the mesh sizing will be used about 3.175 mm with the refined region employed as hex dominant mesh for higher accuracy simulation results. As you can see below here, one of the metal plate is set to a fixed support on one of the end of the plate. At another end of the plate, velocity was applied in the positive x direction to replicate the cross-hit speed during the shear test. And y direction displacement on the bottom of the one lap and one on the top of the other lap. Since we're focusing on thermal, so we use the constant velocity of 1.3 mm per minute, and it's applied for the cross-hit speed. And the temperature used will be about 138 degrees, 178 degrees, 208 degrees, and 238 degrees. So onto the results. As you can see on this first diagram, is the phase diagrams from the DSC machine. I have tested 2 times for each compositions, just to get the average. So for 58% of bismuth, the melting temperature is about 135 degrees, 135.88 degrees, sorry. And for 68% of bismuth is about 138.88 degrees Celsius, and for 48% of bismuth is 147.33 degrees Celsius. So from the results, we can see that bismuth definitely has an impact on the melting temperature.
You have 2 minutes left.
Okay.
Less than 2 minutes left.
Okay, from the lowest is 58% of bismuth, followed by 68% and also 48%. So it's deduced that rich in bismuth, the melting temperature drops, and if less bismuth, melting temperature increases. So this is the wettability results. I used 3 different bismuth compositions as previous, but under the 2 different refill temperatures. So here is for the 180 degrees Celsius, and here is for the 210 degrees Celsius. And as you can see, for 210, the spreading area tends to be bigger. So from this side, I can deduce that different refill temperatures does affect the spreading area. So from here, we could see that 180 degrees gives the best spread as compared to 210 degrees, because 210 tends to overspread the solder. So this is for the single action stress. This is just the deformation of the metal plates of the solder through the axis. And the first graph shows the tensile strength and also temperature graph. Tensile strength increases as the temperature. Tensile strength increases as the temperature increases from 138 degrees until 178. But as the temperature increases, the IMC layer also thickens, which improves this tensile strength. But increasing in IMC layer does.
Can you fasten the presentation a
Sorry.
bit?
Okay.
Time's up. Thank you.
Sorry. High IMC layer, then it would it tends to get brittle. So from there, we can result that high temperature leads to low tensile strength of SMBI. So another graph, just to make it short. This is just basically a tensile strength between, and also the and also the bismuth contents. But just to sum things up, is that by increasing the bismuth does not obviously have the impact. Does not have the impact that you can see here. Okay, there is one. So this is the last one. This is the last graph, shows the series of stress strain graph, where it shows the higher temperature, the higher reductivity of the SMBI. And from here you can deduce that larger BI composition is more, is to deduce that larger bismuth composition is more under the same temperature. Yeah.
Okay.
Yeah, I'm on the demonstration.
Okay, thank you so much. Okay, thank you very much for your presentation, Mr. Elina. Thank you for such information. We will open one question from the floor. Okay, thank you, sir.
Okay, one more question is, did you do some experimental shear stress testing to compare the simulation?
For the shear stress?
Yes.
So far we have not done. This one is only based on I only done simulation tests, because the shear stress is actually under another student, but she does not have the time to do. So the nearest I can get is the simulation test.
So how will you back to predict something value for simulation shear stress? How do you do something so it's just for example the stress is only for simulation. How much is error? It's not to do something compare. It's only based on simulation based testing.
Yeah, simulation based, and also just comparing other research.
Because I think what is validation is.
Okay, has the presenter has answered your question?
No, it's not.
I understand. Okay, any response? sounds?
It's okay.
Okay, thank you very much. Okay, thank you very much, Ms. Nur Elina. Thank you for your presentation. And next we have a third presentation. It's from Dr. Nurizwan Nurdin. He will be presenting an analysis of various heat source models for finite element simulation of WJAM process. So for Dr. Nurizwan, the floor is yours. Dr. Nurizwan. You are given 10 minutes time. We'll be sending the mark at 8 minutes. Okay, the floor is yours.
Test. Test, test. Test.
Test. Okay. Test. Okay. Good afternoon, everyone. My name is Nurizwan Nurdin. I'm actually from English University also, but I forgot to change the logo. So, Dr. Amares is also one of my co-supervisors, and I'm actually not a PhD holder yet. So I'm just Mr. Nurizwan. Today I'll be presenting my study on analysis of various heat source models for finite element simulation of wire arc additive manufacturing process. Okay. Maybe I should sit close to the people. Oh, sorry, the wrong direction. Okay, so let me just go straight. What I'm doing is basically 3D printing. It's 3D printing, but I'm using the welding process, welding method. So I'm sure every one of you have seen the previous presenters. You all know what is wire arc additive manufacturing. Okay, so there are three pictures here. So the one on the left is a key joint. That is a conventional welding specimen. Okay, and on the right there are two pictures. That is the product of wire arc additive manufacturing. So one thing you can see is that in conventional welding there's very little the filler wire. Basically the wire, the metal that you deposit onto the substrate or another structure is smaller than the base metal. But in wire arc additive manufacturing, I'm just going to call it WJAM. In WJAM, there are more. The filler metal is a lot more in volume, in quantity than basically the base metal. So that is quite significant difference. Okay, just going to go straight to the. Okay, so the objective is I'm trying to model this because traditionally we do have welding simulation, but it's for joining. So conventionally we use welding to join metal parts. Now we're using the welding or arc welding to build additive manufacturing, 3D printing, and so on and so forth. Okay, so we have like a traditional heat source that we use in the simulation, but of course conventionally it's used for joining. So is there, or rather, can we change things around and maybe make something simpler that would get as good result or as acceptable result within the margin of error, but something a bit more simpler and less computationally intensive? Okay. So I'm also working on austenitic stainless steel 316L. Okay. In my study, I am using gas metal arc welding, GMAL, and for the simulation, I'm using MSC Meta. It's a general purpose non-linear solver. Okay. The other thing is this is a very simple preliminary experiment, as per the preliminary study before I continue on to do some more deeper experimental testing. Okay, so bear in mind this is a very simple bead on plate, we call it. Okay, so traditionally we use, this is the most popular heat source model, this is the most popular heat input for simulation in finite element analysis, is the gold double ellipsoid heat source model. Basically it looks like an egg, or rather half an egg, and then the heat is distributed normally. There's a Gaussian distribution, and you can also see this. I think everybody who knows gold knows this function. Okay, so this is the standard for like last decade, 2-3 decades. Okay, but there are other possible heat distribution that we can apply or we can use in the simulation. So there's 3 here that I list. There's a uniform, so basically everywhere in the boundary region that you apply the heat source, it's just a constant heat, constant energy. And then there's a parabolic distribution, normal quadratic function. And then this is the normal distribution, or the Gaussian distribution that is used. It also uses Gaussian distribution. Okay, and there is a slight modification that was introduced by software. I can remember Simwell. Okay, so Luz and Norcroft, they basically they modify the Gaussian distribution a little bit, because they find that when they do the simulation, they get a very concentrated peak temperature in the middle. Because when you see the normal distribution, you see there's a very high peak, right? So when you do the simulation, what you find is that you will get a temperature that is much higher than what you will get experimentally if you do the thermal testing with the thermocouple. So they modify it a little bit. If you can see on the left, there is like a flattening at the top, and a little bit. Can I use the word fat? It's a bit fatter. It's a bit wider. Okay, so that is to account for discrepancy between simulation and experiment, where you, if you've done early simulation, you will find that usually you get a peak temperature that is not realistic. Okay, so what he does is introduce this lambda exponent. So if you increase the exponent, you will see that the peak is flattened.
2 more minutes.
Oh yeah, okay. Alright, so you can see that if you increase the lambda exponent from 2 to 4, has to be an even number, 2, 4, 6, 8, 10, it sort of approaches like a square, right? Like it's becoming like a perfect rectangle. Okay, so the question is, can we just simply just use a constant value with some maybe modification and get close enough so that we can save on computational time and we can work on like a bigger mesh, like a more complicated specimen rather than simple specimen? Okay, so what I did was this is just a simulation. At this point in my research, still just simulation. Still in this basically paper is not, there's no experimental stage yet. Okay, so basically this is a simple call it bead on plate. It's just a plate with a simple line of filler material, filler wire. Okay, so what I do is, what I did is I use the usually in finite analysis software you can run your own custom code. You can run it in Fortran. Usually it's in Fortran, and you can do your own function. So that's what I did. We wrote a custom function for 4 different types of distribution, or the heat source model. So uniform, parabolic, Goddard, and then there's the modified Goddard just now. Okay. So as you can see, there's a different. This is cross section. This is fixed geometry boundary. So as you can see, there is different depth, different width as of now, but it's just a visualization tool to further refine the process, the function. Okay. Okay, so this is maximum temperature. Basically, I normalize it to Goddard. Goddard is the standard. So they all have like higher maximum temperature than Goddard, but at the same time they have lower basically total energy. Just calculate the total energy input into the specimen. So this is quite interesting, sort of contradictory in a way. So the next step is to find out why it's like contradictory, and also try to refine the function of the process. Yeah. And even though I said simple, but the actual CPU calculation time is basically the same for all. So I believe there's too much overhead in the user like a compiler module, everything. But going forward, so the plan is that maybe if you want to do a proper apples to apples, orange to orange, just do it in a more direct programming language in Python instead of through like a FEA software where there might be overhead.
Thank you so much.
Okay. All right. So that's it.
Okay, thank you so much, Mr. Norrisman, for your presentation. Thank you so much. We are open for one question. Any participant? Yes.
Okay.
Yeah.
First of all, it's very interesting because I have conducted this model before in my master's studies. Why do you use only this golden model modified? Do you want to use something because for this fine element, you can use the 3 different models to this one case. For example, 3D Con, Golden, and Gaussian's model is 3 different models. Is very popular for art welding or laser welding simulation. So why do you only modify the Golden model?
Okay. Basically, the simple answer is to make it easy for me. But the long answer is
I think it's not much accuracy for art welding because you want to try to 3D Con model and Golden model together.
yeah, it's possible.
Yes,
But I
it's
do
together.
have to
Simulation.
yeah. So basically, in the software I'm using, there's already a module for welding that already has a preset set. Basically, it already has a component for Goddard, double episode, and also conical and yeah, conical. But in order to compare it with the custom code, I wrote the Goddard in Fortran.
Because
Yeah.
this model actually is much error
Mm.
for arc welding because you use FTWJAM, right?
Yeah.
So did you compare some experimental testing or your simulation model?
Will do.
Yes.
Not, but not
Yeah,
this
I
one.
know.
Yeah. So the next step will be to look back at the code. I'm not sure the code is quite good yet, and maybe add in other types of like conical, and then of course compare it to actual supplemental thermocouple with the parallelogram and something. So that
Okay.
is in future plan, but as of right now, this is
All right.
where I am at.
All right. All right, doctor. Is the presenter already answered your question?
Yes.
Okay. Okay. Thank you so much, Mr. Morrison, for your presentation. For your information, we will be having a coffee tea break for 10 minutes. So this time is like 3:42. So we'll break around 3:52. 10 minutes of tea break here. And after the break, we will be continuing with the presentation from Miss Nurul Hanani Abdul Hadi to present her research. So we'll see you in 10 minutes in this place. Okay? Please have a break first. Thank you.